Tonight, we're examining humanity's next step into space. For decades, the plan has been the same. Build a base on the moon, learn how to live off Earth, then use those lessons for the harder journey to Mars. It makes perfect sense. The moon is 3 days away, and we've already been there, while Mars is 6 months away, and we've only seen it through robots. The moon is the logical stepping stone. But what if the logic is backwards? What if we're planning to build our training ground in a place more dangerous than our final destination? By the end of tonight, you're going to see why proximity to Earth means almost nothing compared to the environment itself, and why the familiar world hanging in our night sky might be hiding dangers worse than anything Mars can throw at us. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The moon looks safe. It's right there in our sky, familiar, close enough to reach in 3 days. We've already been there 6 times. Neil Armstrong walked on it in 1969. We planted flags, collected rocks, drove rovers across its surface. The Apollo program proved we could land there, work there, and come home alive. So naturally, when people talk about colonizing space, the moon comes up first. It's the logical stepping stone. Test our technology close to home before venturing to more distant worlds. Build a base on the moon, learn how to survive off Earth, then use those lessons for Mars. That's the conventional thinking. But conventional thinking misses something crucial about what makes a world survivable. Distance from Earth matters far less than you'd think. What matters is resources, radiation protection, gravity, day-night cycles, temperature stability, and geological activity. On every single one of these factors, except distance, Mars wins. Not by a little bit, either. By margins so large that survival on the moon might actually be impossible long-term, while Mars could sustain permanent human civilization. Start with the most immediate threat to any human on the moon: radiation. Earth sits inside a protective magnetic bubble called the magnetosphere. This bubble deflects most of the charged particles streaming from the sun, particles that would otherwise sterilize the surface. The magnetosphere extends thousands of miles into space, shielding everything within it from the constant bombardment of solar wind and cosmic rays. You live your entire life protected by this invisible shield, completely unaware of the deadly radiation that would kill you within hours if it weren't there. The moon sits just outside this protection. At its orbital distance of 238,000 miles, the moon passes through Earth's magnetosphere tail for a few days each month. During that brief window, it gets some shielding. The rest of the time, it's completely exposed. Solar wind hits the lunar surface directly. Cosmic rays, high-energy particles from exploded stars and black holes across the galaxy, slam into the regolith, unimpeded. And worst of all, solar flares can arrive with almost no warning. A solar flare is an explosion on the sun's surface that releases enormous amounts of radiation and charged particles. The really big ones, the X-class flares, can deliver lethal doses of radiation in hours. On Earth, you'd never notice one. The magnetosphere and atmosphere absorb the radiation completely. On the moon, if you're caught outside during a major solar storm, you could receive several sieverts of radiation in a single day. 1 sievert is enough to cause radiation sickness. 5 sieverts will kill half the people exposed to it. 10 sieverts is fatal to everyone. A really powerful solar storm could deliver doses well into the lethal range to anyone on the lunar surface. And here's the terrifying part. The warning time is measured in minutes, not hours. Light from the sun takes 8 minutes to reach Earth and the Moon. When we detect a solar flare, the most dangerous radiation is already on its way. The electromagnetic radiation, the X-rays and extreme ultraviolet, arrives first at light speed. 8 minutes after the flare erupts on the sun's surface, it hits the moon. Then comes the real danger. Solar, energetic particles, protons and heavier ions accelerated to near-relativistic speeds. These arrive anywhere from 10 minutes to several hours after the initial flash, depending on the flare's characteristics. The most energetic particles arrive first. Then comes a sustained bombardment that can last for hours or even days. You'd have maybe 30 minutes to an hour at most before the main particle storm arrives. 30 minutes to detect the flare, sound the alarm, cease whatever work you're doing, and get to shelter. If you're working outside when this happens, you need to get underground immediately. Not into a HAB module with aluminum walls. Those walls do almost nothing against high-energy particles. A typical habitat wall might be a few tenths of an inch of aluminum. That stops the low-energy particles, but is nearly transparent to the high-energy protons and heavy ions. You need several feet of rock or regolith above you to block the radiation. At least 6 feet, preferably 10 or more for the really intense storms. That's the only thing that will actually protect you. That means every lunar base needs extensive underground shelters. Not just one central bunker, but multiple distributed shelters within running distance of any surface work area. Think about what this means, operationally. You're doing a geology survey about 2 miles from your main base. Solar flare erupts. You have 30 minutes. You need a shelter within a 10-minute drive, accounting for rough terrain and the fact that lunar rovers don't go very fast. So realistically, you need emergency shelters every 3 miles or so across your operational area. Each shelter needs to be deep enough, large enough for a crew, and stocked with life support supplies. Each one needs power, communications, and environmental controls. Each one is a significant engineering project that needs to be excavated, constructed, and maintained. And even with all these precautions, people will still be exposed. You can't be underground every second. Work needs to happen on the surface. Repairs, construction, scientific research, mining operations, all of this requires surface EVAs. During those EVAs, you're accumulating radiation dose. Background radiation on the lunar surface is about 0.2 millisieverts per day. That doesn't sound like much. That's roughly 200 millisieverts per year. For comparison, radiation workers on Earth are limited to 50 millisieverts per year. Living on the Moon would expose you to 4 times the maximum allowed dose for nuclear plant workers. Every single year. This isn't a temporary problem you can engineer around. This is continuous exposure that accumulates over time. Cancer risk increases. DNA damage accumulates. Cellular repair mechanisms get overwhelmed. After 10 years on the Moon, a colonist would have absorbed 2,000 millisieverts. That's enough to measurably increase cancer risk by several percentage points. After 20 years, you're looking at significant probability of radiation-induced cancer. And that's just background radiation. That's not counting solar storms. Mars is completely different. Mars doesn't have a global magnetic field anymore. Its core cooled billions of years ago, shutting down the dynamo that once generated a protective magnetosphere. So you might think Mars has the same radiation problem as the Moon. You'd be wrong. Mars has an atmosphere. Thin, yes, less than 1% the density of Earth's atmosphere, but enough to make an enormous difference for radiation. The Martian atmosphere provides the equivalent of about 6 inches of water shielding. That might not sound like much, but it blocks roughly half the incoming radiation. Solar wind particles are mostly stopped. Lower energy cosmic rays are significantly reduced. Even the dangerous high-energy particles that make it through are somewhat attenuated. Surface radiation on Mars is about 0.2 millisieverts per day during solar minimum. During solar maximum, when the Sun is most active, it actually drops to about 0.15 millisieverts per day. That seems backwards, but here's why it happens. During solar maximum, the Sun's magnetic field is more active and tangled. This enhanced magnetic activity actually deflects some of the cosmic rays coming from outside the solar system. More solar activity means less cosmic ray flux. So Mars gets natural variation in its radiation environment that partially self-regulates. The annual dose on Mars works out to about 60 to 70 millisieverts, still higher than Earth. Still higher than radiation workers experience, but manageable. Survivable long-term with reasonable precautions. And here's the crucial part. Mars has caves. We've discovered thousands of them through orbital surveys. Lava tubes formed billions of years ago when Mars was geologically active. Some of these tubes are enormous, hundreds of feet wide, miles long, with intact roofs that have survived for billions of years. Inside one of these lava tubes, radiation drops to near-Earth levels. The rock overhead blocks everything. Cosmic rays, solar particles, everything. Build your habitat inside a Martian lava tube, and radiation becomes a non-issue. You don't need several feet of regolith piled on top of prefab modules. You don't need to excavate massive underground bunkers. Nature already did the work. You just move in. The Moon has no equivalent to this. The Moon has lava tubes too, but they're in the absolute worst locations. Most lunar lava tubes are near the equator, where daytime temperatures reach 260 degrees Fahrenheit. The few polar lava tubes we've identified are small, unstable, or inaccessible. And even if you found a perfect lunar lava tube in the right location, you'd still need to excavate to reach it, seal it, pressurize it, and somehow deal with the Moon's other deadly problems. Which brings us to temperature. The Moon has no atmosphere to moderate temperature swings. Daytime, on the lunar equator, reaches 260 degrees Fahrenheit. Nighttime drops to negative 290 degrees Fahrenheit. That's a temperature swing of 550 degrees. More than 500 degrees Fahrenheit difference between day and night. No other place in the solar system that we might actually visit experiences this kind of extreme. Even Mercury, which is much closer to the Sun, has smaller temperature variations because its rotation period is different. This creates enormous engineering challenges. Your habitat needs to withstand thermal expansion and contraction of materials across this entire range. Metals expand when heated and contract when cooled. Across 550 degrees, that expansion is significant. Seals crack. Joints fail. Structural members warp. You need expansion joints in every structure. You need materials selected specifically for their thermal stability across this range. You need active temperature management systems running constantly. During the lunar day, you're fighting to keep heat out. During lunar night, you're fighting to keep heat in. Both battles consume enormous amounts of energy. And here's the real problem. The lunar day is 29.5 Earth days long. That means 2 weeks of continuous daylight, followed by 2 weeks of continuous darkness. 2 weeks. For the first week, temperatures are rising constantly as the sun beats down on the same spot hour after hour with no sunset to provide relief. By the end of the second week of daylight, everything is heat-soaked. Then, the sun sets and temperatures plummet. For the next 2 weeks, no solar power. No sunlight hitting your solar panels. You're running entirely on batteries or nuclear power. And you're fighting constantly to keep your habitat from freezing solid. Any water in your systems will freeze unless you keep it actively heated. Freeze-thaw cycles destroy pipes and tanks. Electronics that get too cold stop working. Batteries lose capacity in extreme cold. Everything becomes more difficult. You need enough energy storage to run your entire base for 2 weeks. 2 weeks of life support, heating, lighting, communications, everything. That's an enormous battery bank. Hundreds of tons of batteries. Or you need nuclear reactors, which come with their own problems of heat rejection, shielding, and maintenance. Mars has a 24-hour and 37-minute day, barely longer than Earth's. Your circadian rhythm would adapt almost perfectly. You'd have normal day-night cycles, normal sleep patterns, normal human psychological rhythms. And crucially, you'd have solar power available every single day. Your solar panels would charge during the day, then you'd run on batteries at night, exactly like Earth-based solar installations. You'd need enough battery capacity for about 12 to 14 hours, not 2 weeks. The engineering is straightforward. We already know how to do it. Temperature swings on Mars are also dramatic, but nothing like the Moon. At the equator, daytime temperatures can reach 70 degrees Fahrenheit in summer. Nighttime drops to negative 100 degrees Fahrenheit. That's a swing of about 170 degrees. Significant, yes, but manageable. More importantly, the atmosphere helps moderate the transition. Temperature doesn't drop instantly when the sun sets. The thin atmosphere holds some heat. The ground radiates heat slowly. You get a gradual cooling period. Same thing at sunrise. Temperature doesn't spike instantly. The atmosphere diffuses the sunlight. Surface heating is gradual. This makes thermal management vastly easier. Your habitat doesn't need to handle instantaneous 500-degree temperature changes. You can use conventional materials, conventional engineering, conventional thermal control systems. Insulation works. Heat pumps work. Everything works the way we're used to on Earth. And if you build your base inside a lava tube, temperature becomes almost constant. Deep underground, Martian temperatures stay around negative 60 degrees Fahrenheit year-round. Cold, but stable. You insulate your habitat, add heating, and you've got a comfortable shirt-sleeve environment inside, while the outside world does whatever it wants. Now we need to talk about dust. Both the Moon and Mars have dust problems, but they're completely different problems, requiring completely different solutions. Lunar dust is some of the most hostile material in the solar system. Not an exaggeration, not dramatic language for effect. It's genuinely one of the most difficult materials humans have ever had to deal with. It's created by meteorite impacts. The Moon has no atmosphere to burn up incoming meteorites. Every rock, every pebble, every grain-sized particle that approaches the Moon hits the surface at cosmic velocities. These velocities range from about 7 miles per second for slow impactors up to 45 miles per second for the fastest. That's about 23,000 to 148,000 feet per second. For perspective, a rifle bullet travels about 3,000 feet per second. These impacts are happening at 10 to 70 times the velocity of a bullet. When something hits rock at these speeds, it doesn't just chip the surface, it vaporizes. The impact energy is so intense that both the projectile and the target rock turn into superheated plasma. This plasma expands, cools, and condenses back into solid particles. Tiny micrometeorites hit the lunar surface constantly because there's no atmosphere to burn them up. Estimates suggest the Moon accumulates about 100 tons of meteoritic material per day across its entire surface. That doesn't sound like much, spread over 14 million square miles. But it's been happening for 4 billion years. Each impact pulverizes rock into microscopic particles. Over geological time, this creates a layer of powdered rock covering the entire Moon. We call this layer regolith. It's typically several feet deep, sometimes tens of feet in ancient regions that have been exposed to space weathering for billions of years. The Apollo astronauts' boots sank several inches into this powder wherever they walked. These particles are jagged, sharp, and irregular because there's no erosion to round them off. On Earth, dust particles get tumbled by wind and water over millions of years. The sharp edges wear away. Particles collide with each other in rivers and streams. Wind bounces them across deserts. Ocean currents roll them along beaches. All of this mechanical action gradually rounds off the sharp edges. That's why beach sand is smooth and rounded. Each grain has been tumbled for thousands or millions of years. Lunar dust has never been eroded. It's never been rounded by flowing water because there's no water. It's never been polished by wind because there's no wind. Every particle is freshly fractured rock with razor-sharp edges. Under microscopes, lunar dust looks like broken glass. Jagged edges, sharp points, irregular shapes. Some particles look like tiny hollow spheres formed when impact-melted rock cooled. Others look like fractured crystals with sharp angular facets. All of them are abrasive at the microscopic level. When you rub these particles against materials, they act like microscopic sandpaper. And because there's no atmosphere, no moisture, no chemical weathering, lunar dust is also chemically reactive. On Earth, dust particles develop oxide layers almost immediately upon formation. They react with oxygen in the atmosphere. They react with water vapor. They react with various gases and develop stable surface coatings. These oxide layers passivate the particles, making them less chemically reactive. Lunar dust has fresh, fractured surfaces that are chemically active. The surfaces have dangling chemical bonds, unsatisfied valences, reactive sites that want to bond with whatever they touch. This makes the dust incredibly sticky. It bonds to surfaces through a combination of electrostatic attraction and actual chemical bonding. When it gets on equipment, it sticks tenaciously. Simple brushing doesn't remove it. Even vacuum cleaning struggles, because the particles cling to surfaces. When it gets into seals, it abrades them. O-rings that seal joints in spacesuits or airlocks get scratched by the sharp dust particles. These microscopic scratches compromise the seal. Over time, the seals fail, leading to leaks. When it gets into joints, it grinds them down. Rotating joints in spacesuit, arms or legs accumulate dust in the bearings. The sharp particles wear away the bearing surfaces. The joints become stiff, difficult to move. Eventually, they jam or fail completely. The Apollo astronauts reported major problems with dust after just a few days. Each Apollo mission that involved surface EVAs, missions 11 through 17, encountered serious dust issues. Harrison Schmitt on Apollo 17 was particularly affected. He experienced an allergic reaction to lunar dust that got inside the lunar module. His nose became inflamed, his eyes watered, he had difficulty breathing for several hours. The reaction eventually subsided, but it demonstrated that lunar dust isn't just mechanically problematic. It's potentially toxic to human tissues. The fine particles can penetrate deep into lungs if inhaled. The sharp edges can damage lung tissue. The chemical reactivity might trigger immune responses. We don't fully understand the health implications because nobody has been exposed long-term. Apollo astronauts were only on the moon for 3 days maximum. Short-term exposure caused annoying but manageable symptoms. Long-term exposure could cause serious respiratory disease, similar to silicosis in coal miners. Dust got into everything during Apollo missions. Despite efforts to brush it off before entering the lunar module, astronauts always tracked dust inside. It got into air filters, electronics, seals, everything. It was abrasive, clingy, and impossible to fully remove. The spacesuits became contaminated. Dust worked its way into the multi-layer insulation. It got into the joints and bearings. After 3 EVAs over 3 days, the suits were noticeably degraded. Joints were stiffer. Seals were wearing out. If the missions had lasted longer, the suits would have failed. Equipment started malfunctioning because dust contaminated the mechanisms. Cameras had dust on the lenses that couldn't be cleaned. Tools had dust in moving parts that made them difficult to operate. Even inside the lunar module, dust caused problems. It floated in the air in the low-gravity environment. It settled on surfaces. It got into equipment racks and control panels. It got into air filters, reducing their efficiency. It got into electronics, potentially causing short circuits. And this was after just a few days of surface operations. For a permanent base, dust becomes an existential threat. Every time someone goes outside and comes back in, they bring dust with them. It's unavoidable. Even with the most careful procedures, dust will contaminate the airlock. Over weeks and months, the accumulated contamination will spread throughout the habitat. Airlocks need elaborate dust removal systems, multiple stages of cleaning before you're allowed into the main habitat. You need to vacuum suits thoroughly before entering. But vacuuming doesn't remove everything because the dust sticks to surfaces. You need electrostatic dust removal. Systems that use electric fields to pull charged dust particles away from surfaces. But this requires the dust to be charged. and it doesn't work on all materials. You need special coatings that dust won't stick to. Low friction surfaces, non-reactive materials that the dust can't bond with. But we don't actually have coatings that work reliably against lunar dust. Every material we've tested eventually gets contaminated. You need brushes and wipers at every airlock entrance. Procedures where astronauts spend 10 or 15 minutes cleaning themselves before entering. But this just slows the contamination rate. It doesn't eliminate it. You need separate rooms for suit storage, where the contaminated suits are kept isolated from the main habitat. But someone still has to service those suits, which means entering the contaminated zone regularly. You need to completely replace air filters more frequently than you would in a clean environment. The filters get clogged with dust much faster. Each replacement requires new filters brought from Earth or manufactured locally. If you manufacture them locally, you need clean room facilities to make them, which is difficult when dust is constantly infiltrating everything. Here's the fundamental problem. Despite decades of research, we still don't have reliable methods for keeping lunar dust out of habitats and off equipment. NASA has studied this extensively. Research groups have developed prototype dust mitigation systems. Lab tests have been conducted on various approaches, but nothing has proven truly effective at preventing dust contamination. The Apollo solution was to accept contamination and just come home after a few days before things failed catastrophically. That won't work for a permanent base. You can't just accept that everything will gradually be destroyed by dust. You need solutions that work for years or decades. And right now, despite significant research effort and funding, we don't have them. This isn't a solvable engineering problem where we just need to build better equipment. This is a fundamental materials, science, and chemistry problem. We need surfaces that lunar dust won't stick to. We need cleaning methods that can remove all the dust, not just 90% of it. We need protective coatings that don't degrade over time. We need seals and bearings that can function despite dust intrusion. Some of these might be solvable eventually. New materials, new surface treatments, new design approaches. But right now, lunar dust remains one of the biggest unsolved problems for long-term lunar habitation. It's not the kind of problem that gets headlines. It's not as dramatic as radiation or life support, but it's potentially mission-ending. If you can't keep the dust under control, equipment fails, suits fail, life support systems fail, and failures on the moon are fatal. Martian dust is completely different. Mars has an atmosphere, which changes everything about how dust behaves and how it forms. The Martian atmosphere is thin, less than 1% the density of Earth's atmosphere. At the surface, pressure averages about 600 pascals compared to Earth's 100,000 pascals. But thin doesn't mean absent. That thin atmosphere is enough to create wind. Wind creates erosion. Erosion rounds off sharp edges. Martian dust particles have been tumbling in the wind for billions of years. The current Martian atmosphere has existed in roughly its current state for at least 3 billion years. During that entire time, wind has been moving dust around. Every dust storm, every windy day, every gust tumbles particles against each other and against rocks. This constant mechanical action gradually wears away sharp edges. The process is slow compared to Earth because the wind is weaker. Lower atmospheric density means less force from the same wind speed. But over billions of years, Even weak erosion produces significant rounding. Martian dust particles are much smoother than lunar dust, more like Earth's sand, but finer. They're also smaller, on average, finer, more like talcum powder than beach sand. Typical Martian dust particles are about 3 micrometers in diameter, about 0.003 of a millimeter, or 0.00012 inches. Fine enough to remain suspended in the atmosphere for long periods. Fine enough to coat surfaces thoroughly. Fine enough to get into equipment. But not sharp like lunar dust. Under microscopes, Martian dust looks completely different from lunar dust. The particles are more rounded. They still have some irregular features, but nothing like the jagged, glassy shards of lunar dust. They've been weathered, smoothed by billions of years of atmospheric transport. This creates different problems. Dust storms on Mars can cover the entire planet. These global dust storms happen every few Martian years, though not on a perfectly predictable schedule. The last major global dust storm occurred in 2018. It started as a regional storm in late May. Within weeks, it had encircled the planet. The storm lasted for months, not clearing completely until September. During the peak, the optical depth, a measure of how much light the dust blocks, exceeded 10. That means less than 1% of sunlight was reaching the surface directly. The sky turned orange-brown, thick with suspended dust. The sun was barely visible, just a dim glow through the murk. When they occur, global dust storms transform the Martian environment completely. The sky turns opaque. Surface features become invisible from orbit because the dust layer is so thick. Sunlight is reduced by up to 99% at the peak of the storm. Solar panels become useless for 2 reasons. First, they're covered in dust that settles out of the atmosphere. Second, even if they were clean, almost no direct sunlight reaches the surface. The atmosphere is so thick with suspended particles that almost no light penetrates. The Opportunity rover was lost to such a storm in 2018. The rover had been operating on Mars since January 2004. 14 years of service, far beyond its planned 90-day mission. It had survived numerous dust storms, including smaller global events. But the 2018 storm was particularly intense and occurred when Opportunity was already aged. The rover's solar panels accumulated dust faster than they could self-clean. Power generation dropped to critical levels. The rover entered a low-power mode to survive. But the storm lasted too long. Temperatures dropped because the solar panels weren't generating enough power to run heaters. The electronics likely froze. After the storm cleared, engineers attempted to contact Opportunity for months. They sent commands, listened for signals, hoped that the rover might wake up. It never responded. Opportunity was officially declared lost in February 2019. For a human base dependent on solar power, a global dust storm could be catastrophic if not prepared for. If your only power source is solar panels and they're producing 1% of normal output for months, you have a serious problem. Life support systems need power. Heating needs power. Water extraction needs power. Everything needs power, and suddenly you have almost none. This sounds like a deal breaker for Mars colonization. If global dust storms can shut down solar power for months, how can you possibly survive? The answer is preparation and redundancy. First, you know these storms are coming. They happen predictably every few Mars years. you can prepare for them. Second, they start locally and take time to become global. You get warning. Modern orbital observations can detect dust storms when they're still regional. You'd know weeks in advance that a major storm was developing. That gives you time to charge batteries, stockpile resources, and prepare to ride it out. Third, and most importantly, solar isn't your only option on Mars. Nuclear power works regardless of dust storms. Small fission reactors, the kind being developed for lunar and Martian use, generate power from radioactive decay. Dust doesn't affect them. A Mars base would likely use a combination of solar and nuclear power. Solar during normal operations because it's cheaper and simpler. Nuclear as backup for dust storms and for nighttime power when solar isn't available. This redundancy makes the base storm-proof. When a dust storm hits, you switch to nuclear power and wait it out. You reduce non-essential power consumption. You focus on life support and critical systems. You sit tight for a few months while the storm rages outside. Inconvenient, yes, but survivable. And here's the crucial difference from the Moon. Martian dust doesn't stick the way lunar dust does. The particles are smoother, less chemically reactive. They don't have the same tendency to bond to surfaces. They settle out under gravity and can be brushed away relatively easily. More importantly, Mars has wind to blow dust off surfaces. This sounds counterintuitive, since wind is what creates the dust storms in the first place. But the same wind that deposits dust also removes it. Solar panels on Mars self-clean to some degree through natural wind events. Dust accumulates over time, reducing panel efficiency. Then, a windy period comes along and blows much of the dust away. Panel efficiency jumps back up. The Spirit and Opportunity rovers both experience this phenomenon multiple times during their missions. Engineers watching from Earth would see solar panel output declining as dust accumulated week by week. They'd calculate how much longer the rover could operate before power dropped below critical levels. Then, suddenly, output would jump back up. Something, probably a dust devil or localized windstorm, had passed through and cleaned the panels. The rovers called these events cleaning events, and they extended both missions by years. Without natural cleaning, Spirit and Opportunity would have been covered in dust within their first Martian year and unable to generate enough power to operate. But cleaning events kept happening, irregular but frequent enough to keep the panels functional. Spirit operated for over 2,000 Martian days before getting stuck in soft soil. Opportunity operated for over 5,000 Martian days before the 2018 global dust storm. Both rovers far exceeded their design lifetime, operating for years on solar power in a dusty environment. This natural cleaning mechanism doesn't exist on the Moon. There's no wind to blow dust away. Once dust accumulates on a solar panel, it stays there until you physically clean it. Manual cleaning means EVAs, which means exposing crew to radiation and all the other lunar hazards. You'd need to clean panels regularly, maybe weekly or monthly, depending on dust accumulation rates. Each cleaning operation is risky, time-consuming, and uses resources. On Mars, wind does much of the work for you. Not all of it, certainly. You'd probably still need occasional manual cleaning or automated cleaning systems. But the natural cleaning events significantly reduce the burden. Martian dust is also less abrasive than lunar dust. It still causes wear on mechanical parts. Rover wheels on Mars wear down from contact with sharp rocks and abrasive dust. Seals and bearings show degradation over time, but not at the catastrophic rate of lunar dust. The rounded particles don't saw through materials the way sharp lunar particles do. Seals last longer. Joints last longer. Equipment survives longer. And we actually have extensive data on this from the rovers. Spirit operated for over 2,000 Martian days, about 6 Earth years. Opportunity operated for over 5,000 Martian days, about 14 Earth years. Curiosity has been operating since August 2012. As of 2026, that's nearly 14 years of continuous operation. The Perseverance rover landed in February 2021 and is still fully functional. These rovers survived years of exposure to Martian dust with only moderate degradation. Their wheels wore down from the sharp rocks and abrasive soil. The wheels developed holes and tears from driving over rough terrain, but their mechanisms kept working. Curiosity's arm joints still function smoothly after 13 years. The wheels are damaged, but still functional. The cameras still work, despite years of dust exposure. The instruments are still collecting data. This isn't to say Martian dust is harmless. It's definitely a problem that requires engineering solutions. But it's a manageable problem, not an existential threat. Compare that to the Apollo lunar missions, where spacesuits became noticeably degraded after just 3 EVAs over 3 days. After 3 days on the moon, spacesuits had stiff joints, worn seals, and visible damage from dust. After 13 years on Mars, rovers are still mostly functional with degradation, but not catastrophic failure. The difference in material hostility is dramatic and clear from the empirical data we have from actual missions. For a long-term human settlement, this difference matters enormously. On the moon, you're fighting a battle against dust that we don't know how to win. Equipment will degrade faster than you can replace it. Suits will fail, seals will leak, systems will become contaminated. On Mars, you're facing dust problems that are similar to what we deal with in Earth deserts. Challenging, yes, requiring careful engineering and maintenance. But solvable with existing technology and approaches. Water changes everything. The moon has water, but it's all locked up in permanently shadowed craters at the poles. These craters never see sunlight. Temperatures inside them never rise above -250 degrees Fahrenheit. Water ice has accumulated there over billions of years, deposited by comet impacts and formed through chemical reactions between solar wind, protons, and oxygen in lunar minerals. These impacts delivered water molecules that migrated toward the coldest spots. Over geological time, billions of years of this gradual accumulation, significant deposits built up. We've confirmed this ice exists through multiple orbital observations and even surface measurements. India's Chandrayaan-1 mission detected water ice signatures using infrared spectrometry. NASA's Lunar Reconnaissance Orbiter mapped the deposits using radar and neutron spectrometers. The LCROSS impact mission in 2009 deliberately crashed a spent rocket stage into a permanently shadowed crater and analyzed the debris plume. They found water, lots of it, along with other volatiles like carbon dioxide, methane, and ammonia. We know it's there. We know roughly how much. Estimates suggest billions of kilograms of water ice trapped in these polar cold traps. But knowing it's there and being able to use it are entirely different problems. Getting to it is a nightmare. The permanently shadowed craters are among the coldest places in the solar system. Colder than Pluto's surface during its daytime. Colder than most places in the outer solar system. Some crater floors have measured temperatures as low as 25 Kelvin. That's negative 415 degrees Fahrenheit. At that temperature, absolutely everything changes. Any equipment you send in there has to operate at temperatures where most materials become brittle. Steel becomes fragile, like glass. Rubber and plastics shatter at the slightest stress. Lubricants freeze solid. Electronics that work fine at room temperature fail at negative 250 degrees. Transistors stop conducting properly because the semiconductor physics changes at extreme cold. Batteries don't work because chemical reactions essentially stop. Lithium-ion batteries, the standard for space applications, become useless below about negative 40 degrees Celsius, negative 40 degrees Fahrenheit. At lunar polar temperatures, they're completely inert. Solar panels obviously don't work because there's no sunlight. That's the entire reason these craters stay so cold in the first place. Sunlight has never touched these crater floors, not once in billions of years. You'd need to bring powerful lights to illuminate the work area, which requires enormous amounts of power. A work site needs thousands of watts of lighting just to see what you're doing. More power for heating, more for actually running the excavation equipment. All of this power has to come from somewhere. You can't use solar panels inside a permanently shadowed crater. You'd need to position solar panels outside the crater on elevated terrain that gets sunlight, then run power cables down into the crater. Or you'd need to bring nuclear reactors. Small fission reactors designed to operate in extreme cold. These don't exist yet in deployable form, though several concepts are in development. You'd need heating systems to keep equipment functional. Every tool, every piece of machinery, every structural component needs active thermal management to stay above its minimum operating temperature. This isn't a minor challenge. This is a fundamental engineering problem that requires massive energy inputs just to maintain basic functionality. You'd need special materials rated for extreme cold. And you'd need to extract the ice, which isn't sitting in convenient blocks on the surface waiting to be picked up. It's mixed into the regolith as fine grains, maybe a few percent by weight in most locations. The ice is dispersed through the soil, like tiny frozen droplets scattered through dirt. You'd need to excavate tons of regolith, heat it to sublime the water ice, collect the vapor, condense it, purify it. Every step is energy intensive. Excavation requires mechanical systems operating in extreme cold. Heating requires thermal energy to raise the temperature of regolith from 25 Kelvin up to around 200 Kelvin, where water ice sublimates. That's a temperature increase of 175 degrees. The specific heat capacity of regolith means you need about 150 joules of energy per gram just for the temperature increase. Plus the latent heat of sublimation for the ice itself, another 2,800 joules per gram of water. If the regolith is 5% water by mass, you need to process 20 kilograms of regolith to get 1 kilogram of water. That's about 3 megajoules of thermal energy per kilogram of water extracted. For comparison, that's roughly the energy content of 1/10 of a kilogram of gasoline. Except you don't have gasoline on the moon. You have either solar power or nuclear power. Solar power from panels positioned outside the crater, transmitted via cables into the working area. Nuclear power from reactors that you somehow transported from Earth and installed in one of the most hostile environments in the solar system. Then you need to collect the water vapor. It sublimates directly from solid ice to gas because the pressure is so low. You need cold traps to condense it back to solid or liquid. More thermal management, more energy consumption. Then purification, because the ice isn't pure. It's mixed with other volatiles, dust particles, possibly contaminants. You need processing systems to separate clean water from everything else. All of this in pitch darkness at -250 degrees Fahrenheit. Every step requires energy. Energy requires power generation. Power generation in permanently shadowed craters requires nuclear reactors because solar panels won't work. So you need to transport nuclear reactors from Earth across 238,000 miles of space, land them safely on the moon, drive them into craters that have never seen sunlight, and install them in temperatures that make Antarctica look tropical. Then you need to maintain these reactors. Reactors need cooling, which sounds absurd in an environment that's already colder than anywhere on Earth. But reactor cores produce heat that needs to be dissipated. On Earth, we use water cooling or air cooling. On the moon, in a shadowed crater, you have neither. You'd need radiators to dump waste heat, except radiators work by radiation, which is least efficient at low temperatures. The whole thermal management problem becomes a nightmare. And after all that effort, after all that energy expenditure, after overcoming all those engineering challenges, you get water. Essential water, absolutely critical water, water you need for drinking and oxygen and hydrogen fuel. But water you fought incredibly hard to obtain. Water that costs enormous amounts of energy and resources to extract. Water that might be the single most expensive commodity in the history of human civilization, when you factor in the full cost of acquisition. Mars has water everywhere, not locked away in ultra-cold traps, not requiring nuclear reactors to access. Just water, sitting in the ground, waiting to be used. The polar ice caps are mostly water ice, covered with a seasonal layer of carbon dioxide ice. The North Polar Cap is about 600 miles across and up to nearly 2 miles thick in places. That's roughly 400,000 cubic miles of mostly water ice. For scale, that's about half the volume of the Greenland ice sheet on Earth. An enormous reservoir of accessible water. During Martian summer, at each pole, the carbon dioxide ice sublimates away, revealing massive deposits of water ice underneath. The summer sun isn't particularly warm by Earth standards. Peak temperatures at the Martian poles in summer might reach -50 degrees Celsius. That's -58 degrees Fahrenheit. But that's warm enough for dry ice, frozen carbon dioxide, to sublimate. The CO2 layer, which can be over 3 feet thick in winter, completely disappears in summer. Underneath is pure water ice. These deposits are pure enough to use with minimal processing, not mixed into regolith at a few % concentration, not requiring complex extraction processes. Just ice, sitting on the surface, ready to be collected. You could drive a rover to the polar cap in summer, scoop up ice, bring it back to your base, melt it, and you have water. The purity is remarkably high because the ice has been cold-trapped for so long that volatile contaminants have escaped, leaving relatively clean water ice behind. Some processing would still be necessary. You'd want to filter out dust particles. You'd want to test for any unexpected chemistry. But fundamentally, you're working with ice that's close to pure H2O. And it's not just at the poles. This is what makes Mars truly remarkable for water resources. Orbital radar has detected huge underground ice deposits at mid-latitudes. The Mars Reconnaissance Orbiter carries ground-penetrating radar that can see several feet below the surface. It's found ice layers at latitudes between 30 and 60 degrees, both north and south. Some of these deposits are just inches below the surface. A few inches of dry soil, then pure ice underneath. In some locations, erosion has exposed the ice directly. Steep slopes where wind has blown away the overlying soil reveal bright blue-white ice underneath. We have images of these exposed ice faces from orbit. You can see layers of ice, several feet thick, just sitting there, accessible. You could dig down a few inches and hit pure ice. Not permafrost, which is a mixture of ice and soil. Pure ice layers, essentially underground glaciers, left over from a time when Mars's axial tilt was different and ice deposited at these latitudes. The Phoenix lander confirmed this in 2008 when it landed in the northern plains at about 68 degrees latitude. It scraped the surface with a robotic arm. Just about 2 inches down, it hit white material. The science team watched through the cameras as this white material disappeared over the following days. It sublimated, turning directly from solid to gas in the thin Martian atmosphere. Proof that it was water ice and not something else like salt or carbonate deposits. Phoenix even tasted the ice after melting it. Well, the instruments analyzed it chemically. Clean water, no weird chemistry, just H2O with typical Martian dust mixed in. For a Mars base, water is a local resource available almost anywhere you choose to build. You don't need to travel hundreds of miles to special locations. You don't need to operate in permanently shadowed craters. You don't need exotic equipment rated for extreme cold. You can extract water near your base site from shallow underground deposits. The extraction process is straightforward. Excavate down a few inches or a few feet, depending on location. You'll hit ice. Scoop it up. Bring it inside your habitat. Let it warm to room temperature, and it melts. Filter out the dust. Maybe run it through additional purification if you're going to drink it or use it for anything that requires high purity. But the basic process is simple excavation and heating. You could even extract water by heating the soil in place. Drill down to the ice layer. Insert heating elements. Warm the ice enough to turn it to liquid or vapor. Collect the water through the same drill hole. This technique, called in situ resource utilization, or ISRU, has been tested extensively in terrestrial analogues. The engineering is well understood. This is a game changer for long-term habitation. Water isn't just for drinking. Humans need about 3 liters per day for drinking and cooking. But a HAB module needs water for so much more. Hygiene, washing, sanitation, all of these consume water. Growing food requires substantial water. Even with efficient hydroponic or aeroponic systems, plants need water. A small greenhouse, growing enough food to supplement packaged supplies, might need hundreds of liters per day. Then there's life support, redundancy. Water electrolysis can produce oxygen for breathing. You split H2O into hydrogen and oxygen using electricity. The oxygen goes into the atmosphere system. The hydrogen can be used as fuel or vented if you have excess. This gives you a backup oxygen supply independent of mechanical air recycling systems. If your main life support system fails, you can generate oxygen from water while you fix the problem. Water is also radiation shielding. A layer of water surrounding your habitat provides excellent protection against cosmic rays and solar particles. Water has lots of hydrogen atoms, and hydrogen is particularly effective at blocking radiation because it's light and dense in terms of atoms per unit mass. Polyethylene, which is essentially long chains of hydrogen and carbon, is used as radiation shielding for exactly this reason. Water provides similar protection and has the advantage that you can use it for multiple purposes. Shielding today, drinking water in an emergency, propellant feedstock tomorrow. Speaking of propellant, this is where water becomes absolutely critical for spaceflight. Water is hydrogen and oxygen. Hydrogen can be fuel. Oxygen can be oxidizer. Combine them in a rocket engine and you get thrust. Not the highest performance propellant combination. Hydrogen-oxygen has an exhaust velocity of about 14,400 feet per second. Good, but not exceptional compared to some exotic propellant combinations. But it has an enormous advantage. You can make it on Mars from local resources. You don't have to bring it from Earth. Every kilogram of propellant you make on Mars is a kilogram you didn't have to launch from Earth. And propellant is heavy. A rocket returning from Mars to Earth might need 20 to 30 tons of propellant, depending on the trajectory and spacecraft design. Launching 30 tons from Earth costs tens of millions of dollars at current launch prices. Making it on Mars costs electricity and equipment, but no launch costs. This changes the fundamental economics of Mars missions. Instead of launching a round-trip spacecraft from Earth, you launch a one-way spacecraft plus equipment to make return propellant on Mars. The spacecraft arrives at Mars, lands, and immediately begins producing propellant from local water and atmosphere. The Mars atmosphere is 95% carbon dioxide. React CO2 with hydrogen from water and you get methane and water. This is the Sabatier reaction, well understood chemistry used in industrial processes on Earth. The methane can be rocket fuel. The water can be electrolyzed into hydrogen and oxygen. The oxygen is your oxidizer. Some of the hydrogen goes back into the Sabatier reactor to make more methane. You have a complete propellant production system running on Mars using local resources. SpaceX's Starship is specifically designed around this. The Raptor engines burn methane and oxygen, not because methane-oxygen is the highest performance, but because you can make it on Mars. This makes the entire Mars colonization concept practical. Without in-situ propellant production, every Mars mission requires launching enough fuel for the round trip. That might double or triple the launch mass. With ISRU, you only need one-way fuel from Earth. The return fuel is made on Mars. This reduces launch costs by half or more, making regular Mars missions economically feasible instead of financially impossible. And all of this depends on water. Abundant, accessible water that you can extract from the ground near your base without exotic equipment or extreme difficulty. Mars provides this. The Moon doesn't, at least not without Herculean effort. The ability to produce propellant locally also means Mars can become a refueling station for missions going further into the solar system. A spacecraft traveling from Earth to the asteroid belt or outer planets could stop at Mars, refuel, and continue. This extends human reach across the solar system. Ships launching from Earth don't need enough fuel to reach Jupiter. They only need enough to reach Mars. At Mars, they refuel from locally produced propellant, then continue to their destination. This makes deep space missions practical with existing rocket technology. Without Mars refueling, missions to the outer system require enormous spacecraft or nuclear propulsion. With Mars refueling, conventional chemical rockets can reach anywhere in the solar system. Mars becomes the cosmic gas station, the logistics hub for solar system expansion. And that entire capability rests on the availability of water. Water that's sitting in the Martian soil, waiting to be used. Gravity is another massive difference that affects every aspect of long-term habitation. The Moon's gravity is 1/6 of Earth's. Stand on the Moon and you weigh 1/6 what you weigh on Earth. A person who weighs 180 pounds on Earth weighs 30 pounds on the Moon. Mars' gravity is 3/8 of Earth's. That same 180-pound person weighs 67.5 pounds on Mars. That might not sound like a huge difference at first. 67.5 pounds versus 30 pounds, both far less than Earth normal. But the physiological implications are profound and potentially civilization-defining. We know what zero gravity does to the human body from decades of experience with space stations. Astronauts on the International Space Station live in microgravity for months at a time. Some have stayed over a year. Scott Kelly spent 340 days continuously in space, from March 2015 to March 2016. His mission, along with Russian cosmonaut Mikhail Kornienko's parallel stay, provided extensive data on long-duration spaceflight effects. The effects of zero gravity on the human body are severe and well documented. Bones lose density at about 1 to 2% per month. This isn't evenly distributed. Weight-bearing bones, the hips, spine, and legs, lose density faster. After 6 months in space, bone mineral density in the hip can decrease by 10% or more. This is comparable to osteoporosis, a disease that takes years to develop on Earth but happens in months in zero gravity. The mechanism is straightforward. Bones are living tissue that constantly remodel themselves. Cells, called osteoblasts, build new bone. Cells, called osteoclasts, break down old bone. On Earth, gravity loads your skeleton. Every step you take, every time you stand up, gravity pulls on your bones. This mechanical stress signals the osteoblasts to build more bone. The remodeling balance favors bone formation. In zero gravity, there's no mechanical stress. Bones aren't loaded. The osteoblasts get no signal to build new bone. But the osteoclasts keep breaking down old bone at their normal rate. The balance tips toward bone loss. Month after month, bones get weaker. Muscles atrophy, even with vigorous exercise. Astronauts on the ISS exercise 2 hours per day, every day. They use resistance devices, treadmills with bungee cords, to provide downward force, stationary bikes. They work harder during this 2 hours than most people do in a gym workout. Despite this intense exercise regimen, they still lose muscle mass. After 6 months, muscle mass can decrease by 10 to 15%. Again, the problem is lack of constant gravity loading. On Earth, your muscles work constantly just to maintain posture. Standing requires your leg muscles to hold you up against gravity. Sitting requires your back muscles to support your spine. Even lying down, your muscles are slightly tensed. This constant low-level activity keeps muscles toned. In zero gravity, you float. No need to support your own weight. Muscles that aren't used atrophy. The exercise helps, but it can't replace the 24-hour-a-day stimulus of gravity. Cardiovascular systems decondition because the heart doesn't have to work as hard to pump blood. On Earth, your heart pumps blood upward against gravity to reach your brain. This requires significant pressure. Stand up quickly, and you might feel dizzy as your cardiovascular system adjusts. In zero gravity, there's no up or down. Blood distributes more evenly throughout the body. The heart doesn't have to work as hard. Over months, the heart weakens. It becomes smaller, less muscular. Blood volume decreases because the body senses it has more than it needs. When astronauts return to Earth, their cardiovascular systems are deconditioned. Standing up can cause dangerous drops in blood pressure. Some astronauts faint when they first stand after landing. They need assistance, walking. It takes weeks to months for cardiovascular function to return to normal. Fluid shifts toward the head, causing vision problems in some astronauts. This is one of the more recently discovered and concerning effects. In zero gravity, bodily fluids that normally pool in the legs due to gravity redistribute toward the upper body. Faces become puffy. Legs become thinner. The skull experiences increased intracranial pressure because fluid isn't draining downward. This pressure can affect the optic nerve and the shape of the eyeball. Some astronauts develop vision changes during long-duration missions. Nearsightedness, changes in how the eye focuses, physical changes to the shape of the eyeball detected on MRI scans. In some cases, these changes persist after returning to Earth. Vision doesn't fully recover. The mechanism isn't completely understood, but the effect is real and concerning. The spine elongates as vertebrae decompress, causing back pain. On Earth, gravity compresses your spine all day. You're actually slightly shorter in the evening than in the morning because of this compression. In zero gravity, there's no compression. The spine stretches out. Astronauts grow several inches taller in space. This sounds beneficial, but it causes problems. The muscles and ligaments around the spine aren't adapted to this elongated state. Back pain is extremely common among astronauts. Some experience chronic pain that persists even after returning to Earth. Immune system function decreases. Studies on ISS astronauts show changes in immune response. White blood cell counts change. Immune cells behave differently in microgravity. Astronauts are more susceptible to infections. Viruses that are dormant in the body on Earth, like herpes viruses, can reactivate in space. The stress of spaceflight combined with immune suppression, creates conditions for illness. Radiation sensitivity increases, partly because of immune system changes. The combination of radiation exposure and weakened immune response is particularly concerning for long-duration missions. Cancer risk goes up not just from radiation directly, but also from reduced ability to repair DNA damage. After a year in zero gravity, astronauts need months of rehabilitation to recover fully. Scott Kelly required extensive physical therapy after his year-long mission. His bone density partially recovered, but not completely. Some bone loss appears permanent. Muscle mass recovered with training. Cardiovascular function normalized over several months. But the recovery process is long and difficult. Some effects, like bone density loss in certain areas or permanent vision changes, never fully reverse. The body adapts to zero gravity, and not all of those adaptations are reversible. Now, here's the critical question. We don't know what partial gravity does to the human body because we've never tested it. We have extensive data on 1G, Earth gravity. We have extensive data on 0G from space stations. We have no data on 1/6 G or 3/8 G. No one has lived in lunar gravity for more than 3 days during the Apollo missions. Those 3 days aren't enough to see significant physiological changes. No one has lived in Martian gravity at all. We're planning missions to both places without knowing if the gravity levels are survivable long-term. But we can make educated guesses based on the zero-gravity data and basic physiology. The relationship between gravity and bone loss probably isn't linear. It's more likely there's a threshold below which bone loss becomes severe. Think of it this way. Bone responds to mechanical loading. Below a certain loading threshold, bone remodeling tips toward loss. Above that threshold, bone maintains or builds. Where is that threshold? Nobody knows. It might be 1/4 Earth gravity. It might be 1/3. It might be higher. 1/6 gravity, the Moon, might be below that threshold. If it is, people living on the Moon would experience continuous bone loss similar to astronauts in zero gravity. Not as fast, perhaps, but still progressive. Over years, their skeletons would weaken dangerously. 3/8 gravity, Mars, might be above the threshold. If it is, bone would maintain roughly normal density. People could live their entire lives on Mars without skeletal deterioration. We won't know until we actually try. Until someone lives on the Moon for 6 months or a year, and we measure their bone density. Until someone lives on Mars for similar durations, and we compare the results. But the difference between 1/6 and 3/8 is substantial enough that it could mean the difference between healthy, long-term habitation and inevitable physical deterioration. 1/6 might be too low for humans to thrive long-term. 3/8 might be sufficient. The consequences of this uncertainty are enormous. Consider what this means for children. If humans establish a permanent colony on either the Moon or Mars, children will eventually be born there. This isn't speculation. This is inevitable. If the colony is truly permanent, people will have families. Those families will have children. Those children will be the first generation born off Earth. They'll develop in reduced gravity from conception onward. A fetus developing in 1/6 Earth gravity experiences completely different mechanical forces than a fetus on Earth. Bone formation during fetal development depends partly on mechanical stress. Will bones develop normally in lunar gravity? Will they develop the density needed for healthy function? After birth, as the child grows, their entire skeletal and muscular development happens in reduced gravity. On the Moon, they develop in 1/6 Earth gravity. Their bones might not develop the density needed to function in Earth gravity. Their muscles might not develop the strength needed to support Earth normal weight. They could become permanently adapted to low gravity, physically unable to leave the Moon. A lunar-born child might never be able to visit Earth. Their skeleton might not withstand Earth gravity. Standing up on Earth could fracture their bones. Their heart might not be strong enough to pump blood against full gravity. They could be trapped on the Moon for life, not by choice, but by physics. On Mars, 3/8 gravity might be enough for roughly normal development. We don't know, but it's closer to Earth normal than the Moon. A child who grows up on Mars might be able to visit Earth with some adaptation period. They'd need time to build bone density and muscle strength. Maybe months of preparation, intense physical training, possibly medical interventions. But it might be possible. A child who grows up on the Moon might have no such option. The physiological gap might be unbridgeable. This creates an ethical nightmare that we need to confront before establishing permanent colonies. Do you allow children to be born in an environment that might permanently disable them for life on their species' homeworld? Is it ethical to create a generation of humans who can never visit the planet where humanity evolved? What if a lunar-born child needs medical treatment only available on Earth? Advanced surgery, specialized medicine, experimental treatments that exist only in Earth hospitals. If they can't survive the trip to Earth, they can't receive that treatment. They're dependent on whatever medical capabilities exist on the Moon. What if they simply want to visit Earth? What if they want to see oceans, breathe unfiltered air, feel rain, walk in a forest? What if they're curious about the world their parents came from? If their body can't handle the gravity, they're denied that experience. They can read about Earth, watch videos, talk to Earth-born people, but they can never go there themselves. These aren't hypothetical questions for some distant future. If we establish permanent colonies in the next 20 to 30 years, these situations will arise within our lifetimes. Children born on the Moon in the 2050s will reach adulthood in the 2070s. Some of them might want to visit Earth. Some of them might need to visit Earth. And we'll discover whether it's physically possible. The gravity difference between the Moon and Mars could literally determine whether children born off-world have any hope of visiting Earth. 1/6 might be below the threshold for Earth compatibility. 3/8 might be above it. We're making decisions about where to colonize without knowing this critical piece of information. We're betting the future of space-born humans on incomplete data. This is one of the strongest arguments for Mars over the Moon. Mars gravity is closer to Earth. It's more likely to be compatible with long-term human health. It's more likely to allow Earth visitation for Mars-born children. The Moon's lower gravity might create a permanent biological divide between Earth humans and lunar humans. A speciation event driven by gravity difference rather than genetic drift. Geology matters too. The Moon is geologically dead. Its last volcanic activity ended over 1 billion years ago. Its core is cold and solid. There's no tectonic activity, no volcanic outgassing, no geological processes that could provide resources or energy. Everything on the Moon has been sitting unchanged for billions of years. This sounds stable and safe, but it actually creates problems. Without geological activity, the Moon has no internal heat to tap for geothermal energy. Without volcanic outgassing, there's no way to replenish atmospheric volatiles, even if you tried to create an artificial atmosphere. Without tectonic recycling, useful minerals don't concentrate in ore deposits the way they do on geologically active worlds. Everything is evenly distributed in the regolith or locked in ancient rock formations. If you need iron, you have to extract it from regolith. That might be 2% iron by weight. If you need aluminum, same problem. There are no rich ore deposits where tectonic or volcanic processes concentrated metals. Mining becomes an exercise in processing enormous volumes of material to extract small percentages of useful elements. Mars is geologically young by planetary standards. Volcanic activity continued until very recently in geological terms, possibly within the last few million years. Some researchers think certain volcanoes might still be active today. The evidence is indirect. Traces of methane in the atmosphere that could come from either geological outgassing or biological sources. Thermal anomalies detected by orbital sensors. Very young-looking lava flows that show minimal cratering. Whether Mars is currently active or just recently dormant, the geology is vastly more dynamic than the Moon's. This means potential geothermal energy in volcanic regions. It means ore deposits formed by hydrothermal processes when volcanic heat interacted with water-rich minerals. It means concentrated deposits of useful minerals rather than uniform distribution. The Gale crater region, where the Curiosity rover has been exploring, shows clear evidence of ancient hydrothermal systems. Hot water circulated through rock, dissolving and concentrating minerals, creating exactly the kind of chemical differentiation that makes mining practical. Find an ancient hydrothermal deposit on Mars, and you might find concentrated ores of useful metals. Try to mine on the Moon, and you're stuck with regolith processing. The difference in resource availability could be enormous. Communication is another hidden danger of the Moon. This sounds counterintuitive because the Moon is so close. Communication delay is only about 1.3 seconds each way. You can have nearly real-time conversations with Earth. That seems like a huge advantage over Mars, where communication delay ranges from 3 to 22 minutes, depending on orbital positions. But here's the problem. The Moon's rotation is tidally locked with Earth. The same side always faces Earth. This means the far side of the Moon never sees Earth. Ever. If you build a base on the far side, you have no direct line of sight to Earth. Radio signals can't pass through 2,000 miles of solid rock. You need relay satellites to communicate. At least 2 satellites in lunar orbit to ensure constant coverage. Those satellites need power, propulsion for station keeping, and redundancy in case one fails. You've just added massive complexity and cost to your communication system. And if you're not on the far side, but near the poles where the water ice is, you've got a different problem. The sun never rises very high above the horizon at the lunar poles. Earth is always low in the sky or below the horizon, entirely, depending on exactly where you are. Terrain can block your line of sight to Earth. You might need relay systems, even on the near side, if you're in the wrong location. Mars has no such problem. Mars rotates once every 24.6 hours. Earth rises and sets from any point on the Martian surface. During the portion of each day when Earth is above the horizon, you have direct line of sight. You can communicate directly without relay satellites. Yes, the communication delay is longer, but the system is simpler and more robust. You don't need a constellation of relay satellites. You don't need to worry about dead zones where Earth is never visible. And interestingly, the communication delay might actually be psychologically beneficial. When every conversation with Earth has a 3 to 22-minute delay, you're forced to become more independent. You can't call home for advice on every decision. You have to think things through and solve problems locally. This builds the kind of self-sufficiency that a colony needs. On the Moon, the temptation would be to maintain Earth-dependent operations. Constant real-time oversight from mission control. Decisions made on Earth and relayed to the Moon. Colonists following instructions rather than developing autonomy. That's not how you build a permanent settlement. That's how you build an outpost that will never become self-sustaining. The very closeness of the Moon could prevent it from ever becoming truly independent. Let's talk about launch windows and abort options. From Earth to the Moon, you can launch anytime. The Moon is always there, orbiting Earth. You wait for the right position in its orbit, but launch opportunities come every month. If something goes wrong, you can abort back to Earth in 3 days. This seems like a massive safety advantage. Mars is different. Launch windows occur only every 26 months when Earth and Mars are properly aligned. Miss your window and you wait over 2 years for the next one. Travel time is 6 to 9 months, depending on the trajectory. If something goes catastrophically wrong, there's no quick abort to Earth. You're committed for the duration. This sounds terrifying, and it is, but it creates a different kind of safety culture. Moon missions can rely on Earth as a backup. Something goes wrong, you come home. This encourages risk-taking because the ultimate safety net is always there. Mars missions can't rely on Earth. You have to be self-sufficient because there's no bailout option. This forces better preparation, more redundancy, more robust systems. You can't launch to Mars thinking Earth will save you if things go wrong. You have to launch with everything you need to handle any conceivable problem. Paradoxically, this might make Mars missions safer despite the longer duration and greater distance. When you can't rely on rescue, you build systems that don't need rescue. Economic viability is the final piece of this puzzle. Any permanent colony needs to justify its existence economically. Tourism and scientific research won't sustain a settlement forever. Eventually, a colony needs to produce something valuable enough that people on Earth will pay for it. The Moon has one thing going for it, economically: helium-3. This isotope of helium is rare on Earth, but relatively common in lunar regolith, deposited by billions of years of solar wind bombardment. Helium-3 is valuable because it could potentially be used as fuel for fusion reactors. Fusion reactors don't exist yet in practical form, but if they did, helium-3 would be premium fuel. It produces less neutron radiation than deuterium-tritium fusion. The reaction is cleaner and easier to handle. If fusion power becomes real and helium-3 becomes valuable, mining it from the moon could be economically justified. But that's a huge if. Fusion power has been 20 years away for the last 70 years. We might achieve it eventually, but betting an entire colony's economic future on a technology that doesn't exist yet is risky. Meanwhile, the cost of extracting helium-3 from regolith, processing it, and shipping it back to Earth would be enormous. You'd need to process millions of tons of regolith to extract meaningful amounts. The entire operation would require massive infrastructure, huge energy inputs, and constant resupply from Earth until the operation became self-sustaining. And all of this assumes helium-3 fusion becomes commercially viable on Earth. If it doesn't, the whole economic model collapses. Mars has more diverse economic possibilities. Most of them involve supporting further space exploration rather than shipping products back to Earth. Mars could be a refueling station for missions to the asteroid belt or outer solar system. With local water ice and carbon dioxide atmosphere, you can manufacture rocket fuel on Mars. Methane and oxygen. The propellants used by SpaceX's Starship can be made from Martian resources. A ship traveling from Earth to the asteroid belt could stop at Mars, refuel, and continue with a much lighter initial load. This makes deep space missions more practical. Mars could also manufacture radiation shielding, spare parts, and supplies for missions going further out. Martian gravity is high enough to make certain manufacturing processes practical that would be difficult in zero gravity. With abundant solar power, underground space, and local resources, Mars could become the industrial center for solar system exploration. And there's one more possibility. If we discover life on Mars, even microbial life, the scientific value becomes incalculable. Every space agency, every university, every biotech company would want access. Mars would become the most important scientific site in human history. The research infrastructure needed to study Martian life would require permanent bases, extensive laboratories, and continuous human presence. This would economically justify the colony through pure scientific value. So here's where we land after examining every angle. The Moon is close. Mars is far. But distance is the only category where the Moon wins. Radiation is worse on the Moon by a factor of 2 to 3, and the Moon has no natural shelter. Temperature swings are 3 times more extreme on the Moon and occur over 2-week cycles that make solar power impractical. Dust on the Moon is razor-sharp and chemically reactive. Martian dust is smoother and naturally self-cleaning. Water on the Moon is trapped in permanently shadowed craters at -250 degrees. Water on Mars is everywhere, often just under the surface. Gravity on the Moon is 1/6 Earth's, probably too low for long-term health. Mars' gravity is 3/8, possibly sufficient. The Moon is geologically dead, with no concentrated resources. Mars is geologically young, with ore deposits and possible geothermal energy. Communication from the Moon is faster, but requires relay systems. Communication from Mars is delayed, but direct. The Moon allows quick aborts, but encourages Earth dependence. Mars forces self-sufficiency and robust design. The Moon's economy depends on speculative helium-3, mining. Mars offers diverse economic possibilities tied to space exploration and potential biological discoveries. None of this means Mars is easy. Mars is incredibly difficult. The challenges of getting there, landing safely, and building infrastructure in a toxic environment are enormous. But the challenges are solvable with current technology. We know how to build habitats that can handle Martian conditions. We know how to extract water from ice. We know how to generate power on Mars. We know how to grow food in controlled environments. We even know, roughly, how to manufacture fuel for the return trip. The Moon presents challenges we don't know how to solve. We don't know how to keep lunar dust from destroying everything. We don't know if 1/6 gravity is survivable long-term. We don't know how to efficiently mine water from permanently shadowed craters. We don't know how to generate power through 2-week-long nights without prohibitively massive battery banks. These aren't engineering problems with expensive solutions. These are fundamental unknowns that might not have solutions at all. And here's the really interesting part. The Moon's proximity to Earth might actually be a disadvantage for colonization. When Mars colonists face problems, they solve them locally because they have no choice. When Moon colonists face problems, they call Earth. Earth sends supplies, spare parts, replacement personnel. The Moon colony never has to become self-sufficient because Earth is always there. This creates a permanent dependence. The Moon colony exists as an extension of Earth, not as an independent settlement. Mars colonies can't work that way. The distances and time delays force independence. A Mars colony that can't solve its own problems won't survive. This selective pressure pushes Martian settlements towards self-sufficiency much faster than lunar settlements. Over time, Mars colonies become less dependent on Earth, developing their own industries, their own food production, their own manufacturing. They become actual colonies in the historical sense, new societies that eventually grow independent of the mother world. Moon colonies might never achieve this. They might remain forever as research stations or mining outposts, interesting and scientifically valuable, but never truly independent. Imagine the timeline of human expansion to Mars in detail. Picture how this might actually unfold over the coming decades. First Mars mission lands in the late 2030s or early 2040s. Let's say 2042 for concreteness, though the exact date depends on funding, political will, and technical readiness. The mission is probably multinational, a collaboration between NASA, ESA, maybe CNSA, maybe private companies like SpaceX. 6 to 8 crew members, carefully selected for psychological resilience, technical skills, and physical health. They spent 6 to 9 months traveling from Earth. Cramped quarters, recycled air, limited privacy, constant low-level stress. But they made it. They're the first humans to set foot on another planet in over 70 years. The landing site was chosen carefully through years of orbital reconnaissance, probably somewhere near the equator for temperature moderation and sunlight availability, near a known subsurface ice deposit for water access, in a region with relatively flat terrain for easy landing and construction. Maybe Jezero Crater, where Perseverance rover found evidence of ancient water. Maybe Gale Crater, thoroughly mapped by Curiosity. Maybe somewhere we haven't even picked yet, a site that orbital surveys in the 2030s reveal as ideal. The crew spends 18 months on the surface. This duration is dictated by orbital mechanics. You can't just leave Mars anytime you want. You need Earth and Mars to be in the right positions relative to each other. Launch windows occur every 26 months. If you miss your window, you wait 2 years for the next one. So the first crew arrives, works for about 18 months until the next Earth return window opens, then launches back. During those 18 months, they accomplish an enormous amount. They test life support systems under real Martian conditions, not simulations. They practice resource extraction, drilling for ice, melting it, purifying it. They grow food in a small greenhouse, proving that Martian agriculture is possible. They test manufacturing techniques, making building materials from Martian soil. They conduct extensive geological surveys, collecting samples, studying the environment. They test power systems, solar and nuclear, finding out what works and what needs improvement. They practice medical procedures, hopefully not because of emergencies, but through drills and simulations. They document everything exhaustively. Every process, every problem, every solution gets recorded for future missions to learn from. They identify the best locations for permanent bases, places with the best combination of resources, terrain, and accessibility. They establish protocols for Martian operations that future colonists will follow. Most importantly, they prove that humans can survive on Mars. Not just survive, but work productively, maintain their health, and accomplish complex tasks. This is critical for public support and funding for follow-up missions. When they return to Earth in 2044, they're heroes. They bring back experience, data, physical samples, and most importantly, confidence that Mars colonization is possible. Second mission in 2046 deploys the first permanent HAB modules. This mission is larger, maybe 8 to 12 crew. They bring prefabricated habitat modules that will stay on Mars permanently. These aren't the temporary shelters of the first mission. These are serious structures designed to last decades. Inflatable modules that expand to provide living space. Hard shell modules for critical functions like laboratories and airlocks. Power systems, both solar arrays and at least one nuclear reactor for reliability. Life support equipment, water recycling, air recycling, the full infrastructure. Manufacturing equipment for making spare parts and building materials from local resources. Agricultural modules, greenhouses where colonists will grow most of their own food. Medical facilities capable of handling emergencies and routine health maintenance. This crew doesn't come home right away. Some of them are committed to staying for the full 26-month cycle until the next Earth-Mars transfer window. This is the first group of long-duration Mars residents. Not visitors, not explorers, but colonists. By the time they leave in 2048, they've established the foundation of a permanent human presence. The HAB modules are operational and proven. Greenhouses are producing food, maybe 30 to 40% of caloric needs, with the rest coming from packaged supplies. Water extraction is routine, producing hundreds of liters per day from underground ice. Power systems are stable, providing reliable energy through day and night, through summer and winter. Basic manufacturing is operational, producing simple parts and building materials. A second habitat site has been surveyed and partially prepared for the next mission. Third mission, in 2048, brings even more colonists. Some of the original crew returns to Earth. They've done their stint on Mars, contributed to the colony, earned their place in history. They go home to retirement, book deals, speaking tours. But some stay. They choose to remain on Mars, to continue the work they started. These are the first truly permanent Martians, people who committed to Mars over Earth. The population builds gradually, with each subsequent mission. 2050 mission brings specialists in agriculture, engineering, medicine. 2052 mission brings more habitat modules and industrial equipment. 2054 mission brings the first families, couples who committed to raising children on Mars. By 2060, there might be 50 to 100 people on Mars across multiple base sites. Elysium Planitia might have the main colony with 30 to 40 residents. Jezero Crater might have a scientific outpost with 15 people studying ancient Martian geology. The Polar Research Station might have 8 to 10 people studying the ice caps and climate. Each site is semi-independent, capable of sustaining itself, but connected through communications and occasional crew exchanges. They're manufacturing most of their own building materials at this point. Martian brick, made by compressing and heating regolith, is used for construction. Metal is extracted from iron-rich soil and processed into structural elements. Plastics are synthesized from atmospheric carbon dioxide. The manufacturing capability isn't complete autonomy. Not yet. Complex electronics still come from Earth. Specialized equipment, medical devices, high-precision instruments. These are imported. But the basics, construction materials, simple tools, replacement parts for known designs, these are made on Mars. They're growing most of their own food by 2060. Large greenhouse complexes cover thousands of square feet. LED lights provide the full spectrum plants need. Hydroponic and aeroponic systems maximize efficiency. They're growing potatoes, lettuce, tomatoes, beans, wheat, all the staples. Calories are almost entirely locally produced. Vitamins and minerals come from the food they grow. Protein comes from plants, maybe some cultured meat grown from cells, if that technology advances enough. They might still import some delicacies from Earth, coffee, chocolate, spices, things that don't grow well in Martian greenhouses. But they're no longer dependent on Earth for basic sustenance. If Earth stopped sending supply ships tomorrow, the Mars colonists would survive. Uncomfortable? Yes. Lacking luxuries? Definitely. But alive and functional. This self-sufficiency is the definition of a true colony. By 2060, the population could be in the hundreds if things go well. Optimistic scenarios have several hundred people across multiple settlements. Conservative scenarios might have 100 to 200. Much depends on funding, political will, and how well the early colonies perform. If the first decade goes smoothly, investment increases and population grows faster. If there are accidents, setbacks, or failures, growth slows. At this point, Mars colonies start to look like frontier settlements throughout human history. Isolated, difficult, dangerous, but viable. People aren't just visiting Mars. They're living there, building homes, establishing communities, creating social structures. And crucially, children are being born on Mars. The first Mars-born child might arrive as early as the late 2050s. A couple who arrived on an early mission decides to have a child. Medical facilities on Mars have developed enough to handle pregnancy and childbirth. The child is born under 3/8 Earth gravity, the first human to develop entirely in Martian conditions. This child will never set foot on Earth, at least not as a child. Maybe as an adult, if they choose to, and if their physiology allows it. But they'll grow up with red sky as normal, with 3/8 gravity as their baseline. They're not Earth, people living on Mars temporarily. They're Martians. The first generation of true Martians, adapted to Mars, identifying with Mars. By 2070, if Mars colonization continues successfully, there might be 1,000 people on Mars. Maybe more if commercial interests get involved, mining companies, research institutions, even tourism for the ultra-wealthy. At this point, Martian society is developing its own character. They're not just transplanted Earth culture anymore. They have their own challenges, their own solutions, their own social dynamics. They develop Martian slang, Martian customs, Martian identity. They maintain ties to Earth, certainly. Communications, trade, family connections. But they're becoming something distinct, a new branch of human civilization. This is when the settlement truly becomes a colony in the historical sense. Not an outpost, not an expedition, but a new society. Different from Earth, adapted to its own environment, with its own future. Their children will be more Martian than the first settlers. Their grandchildren will have never known Earth except through stories and videos. Mars will be home, not a place they're temporarily visiting. And eventually, probably within a century or two, Mars might seek independence from Earth. Not through war, hopefully, but through natural evolution. When Mars is self-sufficient, when it produces everything it needs locally, when its population is large enough to be viable independently, why would it remain subordinate to Earth? The distance alone makes Earth governance impractical. Communication delay is up to 22 minutes each way. You can't rule a colony when every instruction takes 44 minutes to get a response. Mars will develop its own government, its own laws, its own social contracts. It might maintain friendly relations with Earth, trading, sharing technology, cooperating on scientific endeavors. But it will be politically independent. This is the long-term future of Mars colonization, not just humans living on another planet, but the beginning of humanity's expansion into the solar system and eventually beyond. The Moon timeline would be completely different. Early lunar bases would be larger and built faster because of proximity to Earth. You could have rotating crews, regular resupply, constant communication with mission control. By 2050, there might be more people on the Moon than on Mars, possibly hundreds working in shifts. But they'd all be temporary. Nobody stays on the Moon permanently because the radiation exposure is too high, the gravity is too low, the conditions are too harsh. You do a 6-month rotation, maybe a year, if you're tough, then you go home. The Moon becomes like Antarctica. Scientifically valuable, strategically interesting, but never actually colonized. Research stations and mining operations staffed by rotating personnel who count down the days until they can leave. Important work gets done. But it's not a new civilization. It's an outpost. We've spent most of human history thinking of the Moon as our nearest neighbor in space, our first step to the stars. The logical first destination for any species leaving its home planet. And in some ways that's true. That thinking made perfect sense for decades. The Moon will likely be the first place we build permanent infrastructure off Earth beyond space stations. We'll learn crucial lessons there about living in hostile environments, about dealing with radiation without atmospheric protection, about operating in low gravity for extended periods. We'll develop technologies we'll need throughout the solar system, techniques for resource extraction, habitat construction, life support in airless environments. The Moon serves important purposes. Scientific research, impossible anywhere else. Radio astronomy from the far side where Earth's electromagnetic noise can't reach. Studies of the early solar system from the Moon's ancient surface. Observations of Earth from a unique vantage point. Industrial applications, maybe manufacturing processes that benefit from vacuum and low gravity, maybe materials science experiments, maybe exotic crystal growth or semiconductor production. Testing ground for Mars technologies, proving that systems work before we commit them to missions hundreds of millions of miles away. If water extraction fails on the Moon, we can fix it. If it fails on Mars, people die. But the Moon might not be the purpose we thought it was for humanity's future in space. The Moon might be a training ground, not a destination for permanent civilization. A place to test systems, build experience, develop the expertise we'll need, and then move on to somewhere more survivable. Because Mars is where humanity's future in space really begins, where we build something that can last not just decades, but centuries and millennia. Mars is where we can build something permanent, something self-sustaining, something that could eventually become independent of Earth and grow into its own branch of human civilization. Mars is difficult. Nobody's denying that. The challenges are enormous. The risks are real. The cost is astronomical. Getting there takes 6 to 9 months minimum. Landing safely requires precise engineering. The environment is toxic, the air unbreathable, the temperature cold. Radiation is high, though manageable with proper shielding. Dust storms can blanket the planet. The distance means communication delays and no possibility of quick rescue. Everything about Mars is hard. But every one of those challenges has a solution that exists today or will exist within the next decade or two. We can build underground habitats to avoid radiation, using either artificial excavation or natural lava tubes. We can extract water from the abundant ice deposits just below the surface at mid-latitudes or from the polar caps. We can generate power from solar panels during normal weather and nuclear reactors during dust storms. We can grow food in pressurized greenhouses with LED lighting and hydroponic systems. We can manufacture fuel from atmospheric CO2 and extracted water using the Sabatier reaction. We can produce building materials from Martian regolith and metals from Martian soil. We can manufacture spare parts using 3D printing and local materials. We can create breathable air through water electrolysis and CO2 scrubbing. We can maintain health through exercise, nutrition, and medical care similar to what we already do on the ISS. None of this is easy. None of it is cheap. But all of it is possible with technology that exists today or is in active development with clear paths to deployment. The physics works, the chemistry works, the engineering is challenging but achievable. Compare this to the Moon, where fundamental problems remain unsolved despite decades of research. Lunar dust mitigation has no proven solution, and dust gradually destroys equipment faster than it can be replaced. 1/6 gravity might be below the threshold for long-term human health, creating unavoidable skeletal and muscular deterioration. 2 weeknights make solar power impractical, requiring either enormous battery banks or dependence on nuclear power with no backup option. 500-degree temperature swings create material stress that's difficult to engineer around for long-term structures. Water extraction from permanently shadowed craters at -250 degrees requires technology we haven't fully developed yet. These aren't just hard problems, they're potentially unsolvable with current or near-future technology. we might eventually solve them. New materials science might provide answers we don't have today. But right now, based on our current understanding and capabilities, Mars looks more survivable long-term, despite being vastly more distant. And that's the profound insight this entire exploration reveals. The Moon, Earth's closest neighbor, the world we've already visited 6 times, the obvious first choice for colonization, based purely on proximity, might actually be the harder place to live permanently. Not because we can't get there, we obviously can. Not because we can't build bases there, we've already proven the concept with Apollo. But because the environment itself might be fundamentally incompatible with long-term human habitation in ways that Mars isn't. Mars, distant and forbidding, requiring half a year just to reach, might actually be more hospitable to long-term human presence. More Earth-like in the ways that matter for survival, the ways that might not be obvious from simple distance calculations. Enough atmosphere to block a significant fraction of radiation and create weather patterns. Enough gravity to possibly maintain long-term human health and allow children to develop normally. Enough water to sustain industry, agriculture, and propellant production without heroic effort. Enough day-night cycle regularity to maintain human psychology and enable reliable solar power. Enough geological diversity to provide concentrated resources and possibly even geothermal energy. Enough similarity to Earth's environmental parameters that human adaptation might actually be possible. The Moon's challenges might not be solvable at all. Lunar dust might permanently prevent long-term surface operations. 1/6 gravity might be too low for human health. 2 weak nights might make solar power impractical, regardless of battery technology. Radiation exposure might be unavoidably lethal over decades of residence. These aren't certainties. Maybe we'll find solutions. Maybe lunar colonization will turn out to be practical after all. But right now, based on what we know, Mars looks more survivable. And that's the twist this entire exploration was building toward. The Moon, Earth's closest neighbor, the world we've already visited, the obvious first choice for colonization, might actually be the harder place to live. Not because we can't get there, not because we can't build bases there, but because the environment itself might be fundamentally incompatible with long-term human habitation. Mars, distant and forbidding, might actually be more hospitable, more Earth-like in the ways that matter for survival. Enough atmosphere to block radiation, enough gravity to keep humans healthy, enough water to sustain industry and agriculture, enough day-night cycle to maintain human psychology, enough geological diversity to provide concentrated resources. When the first permanent off-world colony is established, probably sometime in the 2040s or 2050s, the location choice will reveal what we truly learned from a century of space exploration. If we choose the Moon, we're prioritizing proximity over viability. We're picking the close target because it's close, even though it might not work long-term. If we choose Mars, we're prioritizing survival over convenience. We're accepting the difficulty and distance because the destination offers real hope for permanent human presence. My guess, based on everything we've examined tonight, is that we'll do both. We'll build moon bases because they're achievable soon and politically popular. We'll learn hard lessons there. We'll lose equipment to dust. We'll struggle with radiation exposure. We'll face the reality of 2 week nights and 500-degree temperature swings. And after a decade or two of barely sustainable lunar operations, we'll look seriously at Mars. We'll realize that farther isn't always harder. We'll understand that some environments, despite being more distant, are actually more survivable. And we'll make the leap. The first Mars colonists will be remembered as the bravest humans in history. They'll travel for 6 to 9 months in a cramped spacecraft with no possibility of quick rescue. They'll land on a world where the air is poison and the ground is toxic. They'll build their homes underground to hide from radiation. They'll eat food grown in artificial sunlight using water extracted from frozen dirt. They'll communicate with Earth via messages that take up to 22 minutes to arrive. They'll face mechanical failures, medical emergencies, and psychological challenges with limited resources and no possibility of reinforcement for 26 months. And they'll succeed. Because Mars, for all its challenges, is survivable. The resources are there. The gravity is manageable. The day length is right. The radiation is blockable. The water is accessible. The temperature is stable enough. Everything needed for long-term survival exists on Mars. It just needs to be extracted, processed, and utilized by people determined enough to make it work. Tonight, we set out to understand why living on the Moon could be more dangerous than Mars. We examined radiation, temperature, dust, water, gravity, geology, communications, and economics. In every category except distance, Mars came out ahead. Not by small margins, but by factors large enough to fundamentally change the viability of long-term habitation. The Moon remains important. It's close, accessible, and perfect for testing technologies. But Mars is where we build the future. Mars is where humanity becomes a multi-planet species. Mars is where the first children are born, who will never see Earth except as a blue dot in the night sky. Mars is where we learn whether human civilization can exist independently of the world that created it. The Moon is humanity's doorstep. Mars is the next room. And the room after that is the asteroid belt, then Jupiter's moons, then Saturn, then the outer solar system, then eventually, in centuries to come, other stars. But all of that starts with choosing the right, first, permanent colony. Choose wrong, and we might stall for decades, trying to make an unworkable location work. Choose right, and we open the door to the solar system, and eventually, to the galaxy beyond. The choice seems obvious when you look at the evidence. Despite being 175 times more distant, Mars is probably safer. Despite requiring 6 to 9 months to reach, instead of 3 days, Mars is probably more survivable. Despite having no quick abort option, Mars probably offers better long-term prospects. Distance isn't destiny. Environment is destiny. And Mars, for all its hostility, has an environment we can work with. Thanks for spending this time exploring why our assumptions about the Moon and Mars might be backwards. The universe is full of these inversions, places where the obvious answer turns out to be wrong, where conventional wisdom misses crucial details, where careful analysis reveals counterintuitive truths. The Moon will always be special to us. It's the first world beyond Earth that humans touched. Neil Armstrong's footprints are still there, preserved in airless silence. But footprints aren't colonies. Visits aren't settlements. And proximity isn't the same as viability. When we finally build a true home beyond Earth, when we establish a settlement that can survive and grow, without constant support from the homeworld. When we create a community that identifies as something other than transplanted Earthlings, that place will probably be Mars. Not because it's easy, but because it's survivable. And in the harsh mathematics of space colonization, survivable beats close every single time.